This video is on conic sections, and it's the last topic in the vectors, parametrics, and conics unit for pre-calculus. So before we talk about how to manipulate these algebraically, which is what you will be assessed on, I want to talk about what they are and their fundamental use in society. So conic sections are the curves formed when a plane intersects a double-naped right cone, and there are four common conic sections. So before we talk about the double-naped right cone, I want to talk about the applications. So for parabolas, we'll talk about the relationship that a parabola has as far as the points on the curve itself. But how these are used is if you think of a three-dimensional parabola, which is called a paraboloid, these are used for flashlights, headlights and cars, etc. So essentially how a parabola works is that there's a focus, and in a paraboloid, three-dimensional parabola, there's also that focus, but we are able to use that focal point in order to shoot light out of that three-dimensional space going forward. So headlights and cars, that's a paraboloid, flashlights, paraboloid. Any object that you see that is shooting light out in a certain direction and then it expands in that direction, it's most likely using that three-dimensional shape called a paraboloid. The second conic section is called an ellipse. We use ellipses for planetary motion. Such as how the Earth orbits the sun. It does not orbit in a perfect circle. It does bend depending on the direction that it is going, and we can model that using an ellipse, three-dimensional and two-dimensional. And we can also think of light rays. There's other examples out there, but these are the two that people have seen before. Circles, it is a special type of ellipse, and we'll talk about why later in the video. So all circles are ellipses, but not all ellipses are circles. And the last conic section, which is probably the most foreign, is called a hyperbola. And this is used in radial direction, used in radial direction finding, and in the construction of mirrors and telescopes. So these conic sections, two-dimensionally, we can learn some information, but three-dimensionally, they have been part of a bunch of human discoveries and our advances in technology and whatnot. So here's an example of the double-naped cone being intersected by a plane. And depending on the angle that this two-dimensional plane is passing through, will create one of these conic shapes every single time. So if we take that two-dimensional plane, think of a sheet of paper, it's slicing through this double-naped right cone. This double-naped right cone, it's two cones, two three-dimensional cones that are meeting at a point called the vertex. Now, both of these cones they expand in their respective direction infinitely, all right? So we are zooming in at the point where they meet. And this first example shows that we have our two-dimensional plane, sheet of paper, and it's slicing through the bottom nape perfectly horizontal, all right? That will create our circle, our two-dimensional circle. So that sheet in there where they intersect, that will create a two-dimensional shape, which will be a perfect circle. Now, if we were to take this two-dimensional plane or that sheet of paper and tilt it ever so slightly in either direction, we are now skewing that circle, which means one side of it is going to be longer than the other, and that is going to create what is called the ellipse. So we're still passing through only one of the napes, but now if you look, the circle is longer this direction than it is in this direction. And that's when we have what's called a major axis and a minor axis. When for the circle in this first image, we just call it the radius. However, they can also be called the major and minor, but because they're the same, we just call it a radius. Now we can also tilt it so that the sheet of paper, depending on the degree, if you tilt it enough, it will not pass through the nape, it will stay and follow into the nape itself, okay? So we have the example here. Now what's happening is it doesn't close off. It's staying open on one side, unlike the first two images. That's going to create a parabola. And this last one, if we take it and we have it pass through both napes, we end up with two separate shapes. We have a curve at the top, which will go infinitely, and we also have a curve at the bottom, which will go infinitely. So this is when the two-dimensional plane is passing through both napes. And again, any way that you rotate that two-dimensional plane, it will only create one of these four conic sections. All right, so match the picture of each conic section to its name. So the first one here, if you look, there's only one conic section that passes through both napes, and that is the hyperbola. So that will be D. And when we talk about this algebraically, there are a couple attributes for each of these that we will look at. Now, this sketch does not align with what's happening in this three-dimensional diagram. Let's say that we have the center of our parabola at the origin, okay? Sorry, not parabola, hyperbola. Every hyperbola is going to have something called a central rectangle. And we will talk about how to find that. And within this central rectangle, if you look at the corners, you're able to create two linear functions that will create asymptotes for our hyperbola. Now, the hyperbola will follow these slanted asymptotes, all right? So if I were to sketch this curve, the vertex of these two curves is going to be on that central triangle in line with the center. So the curves could either look like this, where they follow the asymptotes. They could be horizontal, or they could also be vertical. So if I had my center, it could be vertical where we have our vertex or vertices on that central triangle in line with the center, okay? Now, we will talk about how to recognize this actually right now, okay? So the first form of a hyperbola from an equation standpoint is that it can open horizontally, which means your vertices will be to the left and to the right of the center. So let's do this. I'll make it match the color. So if it's opening horizontally, that means the hyperbola or hyperbolic curves are following the x-axis, and that means we will have this form. So we'll have x minus h squared divided by a squared minus y minus k squared divided by b squared is equal to 1. So this one opens horizontally because the term with the x is positive, okay? And hopefully you recognize your h and k. Think of your vertex form from Algebra 2. H and k is going to be your vertex for the parabola, but in this case, it's going to be your center. So h and k will be the center for our hyperbola. So let's go ahead and do that. So your center will be hk. Now your central rectangle, that is going to be formed using a and b. And if you notice in the expression, the a is squared and the b is squared. Your a is going to be the horizontal distance from the center. Your b will be the vertical distance from the center. And depending on what type of video you watch, they might switch them. But in this course, I always align a with x, and then I always align b with y. So that way b is always vertical and a is always horizontal. So if we were to have a hyperbola that opens vertically, that means all of the attributes are the same, but now the term with y will be positive. And then I'm going to keep my b squared, so we'll have minus x minus h squared over a squared is equal to 1. And for a proper hyperbolic equation or expression, it has to be equal to 1. All right, the next one is going to be this one. And if we see, this is a closed off shape, so it's not a hyperbola or a parabola, and it's not perfectly rounded, so that means it's going to be our ellipse, and I believe that is B. So for the ellipse, this will also have two types of formulas. However, they will both be positive, okay? So the hyperbola will be the only conic that we go through where you will see an entire term negated. Well, that's not true. You could see the parabola negated. But as far as having a ratio or a fraction involved with both terms, this will be the only one where one of them will be completely negative. All right, so the ellipse, it can either be elongated horizontally or it can be elongated vertically. All right, so if we have an elongated ellipse where it's elongated horizontally, we will have x, we can use x minus h squared and then divided by a squared plus y minus k squared divided by b squared. And again, it needs to be equal to 1. Now, what will make this elongated horizontally is if a is greater than b, okay? If a is greater than b. And if a is greater than b, this is going to be called your major axis because it's bigger. And then because b would be the smaller one, that would be your minor axis. Now, if we had it elongated vertically, we'll write the same equation again. And again, I keep the b. Actually, I'll go ahead and flip it. Let's flip it. Just because you won't always see it in the same order. Now, same thing that I do for the hyperbola. I keep the a with the x and the b with the y. I do the same thing here, okay? So what if your b was greater than your a? Then that means your b would be your major axis and your a would be your minor axis. So that means when we plot these, if we have an elongated or an ellipse that's elongated horizontally, it'll look like this. And then if we have an ellipse that is elongated vertically, it will look like this. Now for the ellipse, we'll solve for two things. We're going to find the center, and using the major and minor axes, we will find the vertices and the co-vertices. So the vertices will be part of the ends of the major axis. The co-vertices will be the end of the minor axis. So in this case, because it's elongated this way, this would be a vertice, this would be a vertice, and then because this is the shorter axis, the minor axis, this would be co-vertice, and this would be a co-vertice. For this image for the hyperbola, this would be a vertice, and this would also be a vertice. So basically the vertices will be where the curves meet the edge of the double-naped right cone. All right, here's the familiar one. This is a parabola, so we'll say A. And a parabola, we're going to have two scenarios for this one, all right? There's a scenario where it can open horizontally or left or right, right? So we could have it open to the right or open to the left. And if that's the case, this should be the one that is less familiar to you because we typically, in Algebra 2, you deal with a lot of functions, all right? This is not a function, all right? We would have to chop half of it off in order for it to be a function and then use those attributes and explore and whatnot. But in the case for conics, it exists left to right and up and down. So for left to right, this is going to be the foreign one. It is x minus h is equal to a times y minus k squared. Or you can also see it as x is equal to a times y minus k squared plus h. So this is your vertex, and then this is just the vertical dilation. So either way is accepted. Now the one that you guys are used to is the parabola opening up and down, because this is a function, so we see it modeled more often. And that's when y is isolated, so it could be y minus h, is equal to a times x minus k squared, or you can see it as y is equal to a x minus k squared plus h. So this is when the parabola is opening upwards or downwards. And again, the vertex is going to be on the edge of the double-naped right cone. So for parabolas, we will find the vertex, which is hk, and we will determine which way does it open. And the last one will be the circle, which is c. So for a circle, we have x minus h squared plus y minus k squared is equal to, we'll say, r squared. And a circle, we're not going to find any vertices, but we're just going to find the center and the radius, because the entire circle, all of the points are on the edge of the double-naped right cone. So that's why we don't locate the vertices, because technically the entire edge of the circle can be considered a vertice. So we'll find the center and the radius. All right, so let's move on to the meat and potatoes of this section and what you will be expected to do on the assessment. So for each general equation provided, rewrite the equation in standard form for a conic and then sketch a graph of the conic. I'm going to push through this pretty quick so that the video is not too long, but if you need to, you can just rewind or slow it down if you need to, okay? So essentially what you're going to be given is you're going to be given an array of terms that are using x and y and a constant, and your job is to manipulate it in a way to where we can get it to one of the four conics that we talked about, so you can recognize what those attributes of the conics are. Now this is a special case. All of the conics, x and y, are squared except for one of them, and that is the parabola. So if we look at this, our y is squared, and then we also have an x, but it's not squared. So that means recognizing that this is going to be a parabola. I can already tell what it's going to be. Now, do I know the vertex based on this form? No. Do I know which way it's opening up? Kind of, because I can see that my y is maybe going to be negative, but we need to get it into standard form in order to see what's going on. All right, so the first step for this is that for a parabola, we want to separate the variables. All right, so I'm going to get all the y's on one side, and then I'll get the x and the constant on one side. So we'll have x minus 10, and then I'm going to add y squared to the right side and subtract 6y. Now, to get to vertex form, I hope you guys remember this. In order to get to the vertex form, we have to complete the square. And just a quick reminder, to complete the square, you take the b value when you're in standard, or in this form, the general form, and then you square it. Okay, so in this case, if we think of ax squared plus bx plus c, our b value is going to be 6. So we will use 6 in order to complete the square. So we have x minus 10 is equal to y squared minus 6y, and then we're going to end up with plus negative 6 divided by 2 squared. Now we have to keep the equation balanced, so since I'm adding this term, I'm also going to subtract it. So we end up with x minus 10 is equal to y squared minus 6y, and then negative 6 divided by 2 is 3. 3 squared is going to be 9, so I have plus 9 minus 9. Now, every time that you complete the square, you are going to end up with a binomial factor, okay? So we can rewrite this binomial factor. We have y squared minus 6y plus 9. We can rewrite that as y minus 3 squared. And every time you complete the square, this is what's going to happen. And then we have minus 9. Now, I'm not quite in standard form yet. I have too many constants, so I'm going to add 9 to the left side. So I have x minus 1 is equal to y minus 3 squared. So now we are in standard form or vertex form, okay? And I can see that this is my h value, so h is going to be positive 1, and then my k is going to be positive 3, and that is going to be our vertex. All right, so that is part A. So part B, we have a parabola with a vertex that is located at 1, 3. And we know which way it's opening based on standard form. So it's opening, based on its standard form, I see that it is y squared. All right, so if it's y squared and positive x, if I think about my basic parabola, and maybe that's what you have to go back to. I have y equals x squared. That's our parent function. It opens upward. So if you look, it's hugging the positive y-axis, and then we have, for each y value, there are 2 x values, hence the squared. So for the one that we are looking at, it's going to hug the positive x-axis. Therefore, each y value will have 2 values for each x. Okay. So it's opening to the right because of the y squared. So if I do a quick sketch, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The vertex is at 1, 3. And then it's a very rough sketch, so then I'm opening in this direction. And that's it. Now, in the notes that I post in Google Classroom, you'll see some side notes about parabolas and why it's a parabola, but in the context of this course, you only have to worry about rewriting it into standard form and then recognizing the attributes. All right, the next one, we have x squared minus 10x plus y squared plus 4y plus 13. So this one, we can see that both of the terms are squared, and they are also positive, okay? So in order for this to be a hyperbola, one of them would have to be negative. Everything's on the same side. One of them would have to be negative in order for it to be a hyperbola. So it's not a hyperbola. It's not a parabola because they're both squared. So it's either an ellipse or a circle. I don't know yet. We won't know until we get it to standard form. So let's do it. Okay, so for an ellipse and a circle, if we go back up here, neither of them have a constant, an isolated constant on the left side. All right, so let's move our constants to the right. So I have x squared minus 10x plus y squared plus 4y. I have that 13, so I'm just going to do equals negative 13. Now, the goal for all of these is to create these binomials, these squared binomials. I could already see that that 13 was not going to fit with the x squared minus 10x, nor was it going to fit with the y squared plus 4y. There was no way I was going to create a binomial for that. So I need these binomials, so I'm going to complete the square twice. All right, so once for x and then once for y. So I have x squared minus 10x. I'm going to do plus, I have negative 10 divided by 2 squared. And since, actually, we need this constant for the binomial here, so we'll keep it here. And then we'll have plus y squared plus 4y. Completing the square for y, we'll have 4 divided by 2 squared. So the reason why I'm keeping these two constants over here is because I need them in order to create the binomials to get it to standard form. On the right side, I have negative 13. And in order for me to keep this balanced, I'm going to add the negative 10 over 2 squared on the right side, and I'm going to add the 4 divided by 2 squared on the right side. Up here, we left it on the same side, but eventually we did move it to the other side. All right, so we could have added it to both sides and get the same effect. All right, so what happens here is we end up with x squared minus 10x. 10 divided by 2 squared is going to be 25. And then we have plus y squared plus 4y, and then we get the 4 here. So we get negative 13 plus 25 plus 4. All right, the binomial here, we have negative 10 and then positive 25. So we'll have x minus 5 squared. And then for the y, we have positive 4, so this will be y plus 2 squared. And then on the right side, we end up with a 16. So this is going to be a circle. And I can tell it's a circle because we do not have any ratios. We didn't have to divide anything or isolate anything, so we're good. Now, if you did divide everything by 16, you would end up with this, where it's divided by 16 is equal to 1. So technically, if you want to set all of your conics equal to 1, you could. But for this one, it's not really efficient because the major and minor axis is the same. It's 4, which means this is just a circle. So that's why we just leave it as equal to 16. All right, that's part A. So now part B, we'll go ahead and get a sketch. This is a circle with the center is going to be the opposite of what we see in our standard form. So the center is going to be at 5, -2. And then the other attribute is the radius, which is 4. And that's because 16 is equal to r squared. Therefore, 4 is equal to r. So again, a rough sketch of this. The center is at 5, -2, so that's going to be in the 4th quadrant. And then the radius is 4, so if I do 5 plus 4, that'll take me 9 horizontally. So 1, 2, 3, 4, 6, 7, 8, 9. And then we should be good on this side. We're going up to the center's at -2 plus 4, that's +2. And then we'll expand to -6. All right, so the center is going to be 1, 2, 3, 4, 5, -2. Again, this is very rough. And then, let's see, my radius is going to be 4, so I'll go up. 1, 2, 3, 4. And then in this direction, 1, 2, 3, 4, I'll get to 1. Going down, 1, 2, 3, 4. And then 1, 2, 3, there it is, 2, 3. Scaling's a little off, but it doesn't have to be perfect. And then we have our circle. And this has a radius of 4. So what I meant to do was, we have our parabola here. So a way that you can check this, you won't get Desmos on your test, you'll have your TI, but I guess this isn't on the AP exam. So this is just here to help you visualize it. I hope it didn't reset it. It did. Okay, so I had all of these put in. Oh, it reset it again. It's resetting all of them. All right, great. Thanks, Desmos. You can type these in the Desmos, and you can compare this form to your standard form and see if they align. So if you end up doing the practice work, you can use Desmos to help see if you got it correct visually. All right, we have 2 more, and then we'll be done. So with this one, we have 9x squared plus 54x minus 4y squared plus 16y plus 29. So there are a few different things happening here. First off, we have coefficients. We have coefficients with our leading terms, which means we are going to end up having to divide. All right, so this won't be a circle because we didn't have to divide. And it could be an ellipse. Actually, no, it can't. Because for an ellipse, both terms are positive. The x is positive and the y is positive. So we have one that's negative this time. Can't be a parabola because now both x and y are squared. So that means we are dealing with a hyperbola, okay? So whenever we see our leading terms with coefficients, you're going to be dividing, which means it's probably not going to be a circle unless those coefficients are the same or some algebraic manipulation gets us back there, okay? So I'm going to guess hyperbola. All right, and again, we have to get to these squared binomials, so we will have to complete the square, so we need to get the constants to the other side. But luckily, we only have 1. So we'll have 9x squared plus 54x minus 4y squared plus 16y is equal to 29. Okay, so let's see. Well, to make this easier for you, for the x's, we can factor out a 9. For the y's, we can factor out a 4. So let's go ahead and do that now. So we factor out a 9 because eventually you will need to isolate your leading terms so that they have a coefficient of 1. Okay, so we'll factor out the 9. 54 divided by 9 is 6. And if we complete the square here, which we're going to have to do anyway, 6 divided by 2 is 3. 3 squared is 9. And now for the y terms, we will factor out negative 4 because I don't want that y squared to be negative, so I'm going to factor out negative 4. So now we have y squared. When you factor out negative 4 from 16, 16 divided by negative 4 is negative 4, so we have negative 4y. And then completing the square, we have negative 4 divided by 2, which is negative 2. You square that, you get positive 4. And then we have our constant 29. Now I have my plus 9 over here and my plus 4, so I need to do that to both sides. So we'll have plus 9 plus 4. There we go. Okay, so we have 9 times, when we create our squared binomial, we have a positive 6 and a positive 9. That's going to be 3. So we have x plus 3 squared. And then we have our minus 4. We have a negative 4 and a positive 4. So this is going to be y minus 2 squared. Because negative 2 times negative 2 is positive 4. And then on the other side, we have 29 plus 9 plus 4, which is 36. So I know this won't be a circle because we have these coefficients out here. So we are going to have to divide and set this equal to 1. Okay, so when you see these coefficients, that's going to be for ellipses and hyperbolas. So divide by 36, divide by 36, divide by 36. So I can reduce this. This is going to be x plus 3 divided by 4, x plus 3 squared divided by 4, minus, I can also reduce these. This will be y minus 2 squared divided by 9. And if you see this relationship here, that always happens. It'll always happen. Set equal to 1. And that is the standard form for our hyperbola. So now the question is this going to open up horizontally or vertically? We can see that x is positive, so that means the two hyperbolic curves are going to hug the x-axis in some way, shape, or form. So part B, we need to draw a sketch of this. I'm going to have a pretty large sketch over here. So we have a hyperbola with, we need our center. Our center is going to be negative 3, positive 2. And that's based on the numerators. So x plus 3, we have a solution of negative 3. Y minus 2, we have a solution of positive 2. So if we sketch this, we will start in quadrant 2. And I'm going to negative 8 horizontally and vertically. Okay, so our center, we have negative 3, positive 2. We'll draw a little x for that. Now, for a hyperbola, to get it's a rough sketch, but you want the sketch to be accurate, we use a central rectangle. Central rectangle. And for the central rectangle, we need the width, which will be A, and we need the height, which will be B. So my A will always be with my X because that's telling me how far from the center am I traveling left and right, and that's going to be your A value. So this 4, this is A squared, so that means my A is equal to the square root of 4, which is 2. So that's the horizontal distance. So I'm going to go ahead and sketch that in. I'm going to travel 2 to the, wait, we went up 2, right? All right, so 2 to the right, and 2 to the left. Now, I already know my hyperbola is opening up horizontally, so that means my vertices will be at the end or on the edge of my central rectangle here. And then the height of this rectangle from the center, I see that my 9 is b squared. So if we take the square root of that, we get 3, and that's the vertical distance from the center. So I'm going to go up 3, 1, 2, 3, and then down 3, which will take me to -1. Okay, so when we get these, you can sketch your rectangle from here. So we have this. Sorry, my scaling's a little off. So I'm going to go ahead and bold the central rectangle just so we can see it. There we go. So this is our central rectangle. And essentially what we use this for is for the vertices of our hyperbolic curves and the asymptotes that they will be approaching indefinitely. So to create the asymptotes, you'll start from the center, and then you will extend through the corners of the central rectangle. Okay. And the last part is drawing the curve itself. You'll start at your vertices, and then you'll draw the curve so that it approaches those asymptotes. And there's the rough sketch. All right, the last one and the final one that we haven't seen yet is the ellipse. And I can recognize this will be an ellipse because I have two squared terms. They're both positive and they have two different coefficients, right? So we can assume that this will be an ellipse. So part A, same exact steps. We're going to isolate the constant, and then we will complete the square for each of the variables individually. So again, we can factor out 9 for the x's and then factor out 25 for the y's because we want to isolate the leading terms. So you can do a lot of these steps simultaneously, which is what we're going to do for this one since it's the fourth time. So we have 9 times x squared plus 18 divided by 9 is going to be 2. Complete the square. We have 2 divided by 2, which is 1. 1 squared will be 1. And then we have plus, if we factor out 25, we get y squared minus 200 divided by 25 is going to be 8. If we complete the square, we have -8 divided by 2, which is -4. -4 squared will be 16. And then on the right side, we subtracted that -184. And we have to add the 1 and add the 16. All right, so creating these binomials, these squared binomials, we need a value that adds up to 2 but multiplies to 1. So that's going to be x plus 1 squared. And then we have our 25. And then we need a value that adds up to -8 but multiplies to positive 16. That will be y minus 4 squared. So for that constant there, let's go ahead and put plus 2 or minus 208. Minus 208. So then that means this will be plus 208 plus 1 plus 16. And we end up with 225. That way we end up with integer values so we can sketch this accurately. Sorry about that. So now from here, we can see that this is not a circle, so we have to divide and get it equal to 1. So we'll divide all terms by 225. When we do that, we talked about the relationship. Like with this hyperbola, we saw that essentially whatever we factored out just ended up the denominator for the other term. That's going to happen again here. So we'll have x plus 1 squared divided by 25 plus y minus 4 squared divided by 9 is equal to 1. So we see that both terms are positive, and we have our ellipse. Part B. So it's an ellipse with the center is going to be at -1, 4. And then we have two axes. We have our major and our minor. So in this case, we see that we have a larger denominator with the x, which means the horizontal axis will be the major axis. And again, this is a squared, so that means a is going to be equal to 5, and that's going to be the distance from the center to the horizontal vertices. So it's horizontal, and it's also the major because it's larger. And then our b value, this is b squared, so that means the vertical distance from the center is going to be 3. So this is vertical, and it's minor. All right, so if we do a sketch of this, we are kind of in quadrant 2, yeah. All right, and the center is at -1, 4, so we'll be up here. And then I might need to extend my vertical axis, we'll see. All right, so our horizontal axis, or our major axis, has a distance of 5 from the center in both directions. So we'll have 1, 2, 3, 4, 5. And on the other end, we're at -1, so we'll go to -6. 1, 2, 3, 4, 5, 6. So we'll go out to here. Now, at the edges of the major axis are going to be your vertices. So we read left to right, so I call this one V1, and then I call this V2. So in my list down here for vertices, V1 is going to be -6, +4. So all I did was -1 minus 5, and then -1 plus 5, we end up with +4. And then the height is 4 because it's in line with the center. Now vertically, we're going to go down 3 and up 3. So I'll go down to here, and then I'll go up to here. So I list covertices top to bottom, CV1 and then CV2. So CV1 is, if we start at the center, well, it's going to be in line with the center. It's going to be at -1, but then we start at 4 for the center, and then we will add 3 because we went up 3. So 4 plus 3 is 7. And then for covertice 2, we're still in line with the center. So we'll do 4 minus 3, which is +1. And then we can draw the little curves in here. That's terrible. There we go. All right, so on the test, you will not be expected to sketch. This is just so you can get comfortable with them. However, you will be matching graphs with the correct equation, or you might be given attributes that you have to align with the correct equation. So you're not going to sketch, but hopefully it helped you to recognize what you will be looking for, okay? I hope this helps. If you have any questions, please email me. Thank you.